This is the Chapter 14 review, and we will begin with question 1. The correct name for this compound is shown below is what? Okay, well, notice that we have MOP and another O. So what M stands for, that M is going to be equal to meta, right? So that's meta. O is going to be equal to ortho, and P is equal to para. But what does this mean? Well, it just shows you the location of the substituents, okay? So over here, this substituent right here, well, you could say let's just go with this. So because we have an alcohol, we're going to name the whole compound after the alcohol, which is how you get phenol. Okay, well, the substituent right here would be chlorine. And the way it goes is that first it goes ortho, then it goes meta, and then it goes para. Okay? So the way I remember it is that para is going to be parallel to the compound name, right? So it's going to be parallel to alcohol. M is just kind of like offset, right? So it's basically 2 away from the alcohol. And then ortho is right next to the alcohol. Okay? So again, this would be ortho, this right here would be meta, and this would be para. So using what you already know, what's the correct answer choice? We know that our answer has to have something with phenol, right? So it's not alcohol, not D, it's not E, because whenever you have an alcohol on a benzene ring, it becomes a phenol. So it's either A, B, or C. But where's my chlorine? Well, my chlorine is on the ortho. So I should be having orthochlorophenol, right? So it should be B. Now number 2, what is the correct name for this compound? Well, we have our answer choices, which has aniline, or aniline, right? So aniline is going to be this compound right here. Now, you may see amine. Well, amine is NH2, but we only use amine when there is something else that is more important. For instance, if I had a carboxylic acid, then my NH2 would be an amine, okay? It's kind of like a sub-name. But if the NH2 is the most important thing in the compound, we're going to call it an aniline. And in this case, it's the most important thing. So I know my answer choice has to have something with aniline. Now, where is my bromine? My bromine is on what? Well, this carbon right here is called the ortho, and then this compound right here is called the meta, and over here, which is parallel from the aniline, would be para. So I know that my bromine is meta. Okay, well, it would have to be answer choice A. We have meta, bromo, aniline. Okay, so it's A. Now over here, what do we have? Okay, well, first of all, we don't have an alcohol. Okay, we don't have an alcohol in this compound. So no matter what I do, I can never have a phenol, right? That wouldn't make any sense. So E is wrong. What about toluene? Toluene, if you remember correctly, is basically a benzene ring, except it has a methyl group on it. Okay, so that's a toluene. Do we have that? No, we have kind of like an ether right there, but there's no methyl group coming out the benzene ring, so I know toluene is not right. So it has to be anusol. So what is anusol? Anusol is basically an ether. It's this guy right here. That's an anusol, okay? So what is this guy right here? Well, that's called a nitro. Alright, so that's basically what you get over here. This is what you're seeing. We have nitro, right? And that is this compound. Okay, well, we know that this is going to be O, this is M, and this is P. Notice how the nitro is parallel to the anusol. So it has to be answer choice C, because we are parallel to the anusol. Okay. Now number 4, what about this one? Well, notice that this is a benzene ring. And if we ignore the bromine, we have a methyl group coming out the benzene ring. And that's called a what? It's called a toluene, okay? And what is next to the toluene? Well, a bromine. Okay, so we already know that this would have to be O, right? So that's O, so it has to be what? O-bromotoluene, has to be D. This doesn't make sense because, well, this is the IUPAC name, but do we really work with that in this class? Bromomethyl benzene? Like, doesn't sound good. And why would you make this bromine a 3? Like, you would name it the least substituted one, right? So we would give it the lowest numbers. Why would you have 4 on it? That doesn't make sense. And O, yeah, that would make sense for us. And so basically, just treat the methyl group like an anusol. You treat it like a nitro. You treat it like any substituent, okay? You don't treat it like a carbon that you count from. No, you count from this carbon and do that, okay? So technically, if you wanted to do it, it would be like a 2-bromo whatever, not a 3-bromo. Which of the following is not, keyword not, 2-bromo 5-nitrobenzoic acid? Well, the way I like to work with these problems is that I notice what we're working with in the back. So we're working with benzoic acid. Well, benzoic acid, if you have an ick, and then you have, oh, let's redo this. So we have a oic acid that goes to carboxylic acid. So carboxylic acid. And of course, we know we have to bring the bunny every time. He's very happy. Let's do that. Yeah, there we go. Okay, well, if we're looking for carboxylic acid, that's what I have to look for. But let's just find out. So here's a carboxylic acid right here, right there. Okay, so it's in every answer choice. And basically, once you have the parent name, you want to count from that carbon. Okay, so let's go for number 1. This is the carbon that I'm going to start counting from. So that's number 1. Okay, so that's 1. This is 2, 3, 4, 5. Okay, well, basically I have what? I have my nitro NO2 on the 5th carbon, which is good. And then I have my bromine on the 2nd carbon, which is nice. And then my benzoic acid, or I should say my carboxylic acid, is on the 1st carbon. Well, this checks out. So it cannot be number 1 because we're looking for a compound that is not 2-bromo 5-nitrobenzoic acid. Okay? So again, I'm going to start counting from this carbon. 1, 2, 3, 4, and 5. Again, that's not going to work for me because this is the correct answer choice. So that's bad. What about this one? Well, let's do 1, 2, 3, 4, and 5. Bad again. 1, 2, 3, 4, 5, and then 6. Wow, so my nitro is actually 6. So this would be what? This would be a 2-bromo 6-nitrobenzoic acid. Okay, so this is the correct answer choice. Answer choice D, or number 4, would actually be the correct answer choice. Again, whenever you're working with these problems, just notice what's the parent name. Oh, I have an oic acid. That must mean that the carboxylic acid is going to be the 1st carbon. So, for instance, this would be carbon number 1. Then we go to carbon number 2, 3, 4, and 5. Again, number 5 would be wrong. So, it'd be D. Number 6. So now we have to name this compound. Okay. We'll notice that we have the NH2, and you should know that NH2 is going to be called an aniline. So NH2 is called aniline. And if it's not important, it also could be called an amino. That's kind of like if it's a child. So for instance, if we had a carboxylic acid, the NH2 would be called an amino. Okay, and then it would be in the front, not in the back of the name. Okay, so whenever something is in the back of the name, you know it's the parent is going to be the most important. Okay, so we have to name the correct compound. Okay, well, notice that I'm going to, since this is the most important substrate or substituent, I'm going to call this number 1. And then I'm going to have to number my other substituents. So am I going to do 2, 3? Well, no, because my 2nd carbon is just a carbon, but if I go here, my 2nd carbon has a bromine. And again, I want my substituents to be on the lowest numbers. So that's 2, 3, 4, and 5. So I have 2, 5, and I have 2 bromine, so that's going to be di for 2, dibromo, bromo, and we don't say benzene. Instead, we're going to say aniline. So we're going to say aniline or aniline, whatever you want. So is that an answer choice? Yeah, it's answer choice C. So we have 2,5 dibromo aniline or aniline. So that is answer choice C. Number 7, 4-amino 2-bromo anusol. So anusol, you're going to have OCH3, right? So that's anusol. And if you speak Spanish or know that sol, S-O-L, is sun, you can imagine kind of like the oxygen right here is like the sun, and CH3 is just CH3. Okay, so it's kind of how I remember it. So number 7, I know that I have an anusol, so here's my anusol, right? Over here on number 3, I know that this is wrong. Where's my CH3? Right, that's just an aldehyde. That's not going to work for us. So I can automatically eliminate 3. Anything else? No? Okay. So anusol means I'm going to start counting from this carbon. So we're going to do this carbon. We do, let's see. Actually, number 1 would not be an anusol because this anusol is connected to a carbon. You see, it's like this. Number 1 has carbon, carbon, O, and then CH3. Right? This is bad. Okay? Because this carbon should be connected to OCH3. Where this carbon is kind of like the benzene ring, right? So that's the benzene ring. Notice that we have a bridge over here. That's not right. Okay, so number 1 is wrong automatically. So let's just do this. So 1 is wrong, right? And let's see. We want 2-bromo. Well, no matter what I do, my bromine is never going to be near my anusol for number 2. Okay? Notice that my bromine would actually be on 1, 2, 3, 4. It would be on the 4th bromine or 4th carbon. That's wrong. So it's either 4 or 5. Okay, well, let's see. We do. Notice how this oxygen is directly attached to the benzene ring. That's an anusol. The reason why this oxygen is not an anusol is because it's attached to another carbon. And that carbon leads to the bromine ring, or benzene ring, sorry. So we go 1, 2, 3, and 4. Okay, well, this looks pretty good for me, but let's check our answer. Let's do 1, 2, 3, and 4. Okay, well, you're saying, well, Brian, they're both pretty close. What's the difference? Well, the difference is that over here you're dealing with NH2, and over here you're dealing with NO2. Okay, so we have our anusol, and then we need amino, and amino is NH2. This right here is called a nitro. So this is a nitro, which is bad. Okay, so this is bad. So number 5 is bad. It would be number 4, or D. Okay. 8. Which reagents would serve as a basis for simple chemical tests that would distinguish between benzene, it's benzene right here, and 1-hexene? Let's just do it over here. Okay, so what can we use? Well, without getting into too much detail, you should know that benzene can only do substitution. Okay, never addition. And by that, I mean, basically, you have 2 hydrogens right here, right? And for benzene, it can actually take out those hydrogens and replace it with an alcohol or replace it with bromine or whatever. That's okay. But if we do an addition, that means that I'm still going to have my 2 hydrogens and then I'm going to add something like an alcohol, or I'm going to add a bromine. So let's say that this is my alkene right here, and they have some hydrogens. Well, if you do this, and let's just do an alcohol right here, and then this right here, an alcohol. Well, we added something. We got rid of the double bond, and we added an alcohol. Well, benzene can't do that, but 1-hexene can, right? Instead, what happens if I did this? What happens if I got rid of my double bond and instead had an alcohol? Okay, and then I did another alcohol. Well, I substituted my hydrogens for what? For alcohols, and benzene can do that. That's alright. So let's try to make some more room so we can do this reaction. Okay, so let's start with number 8. Well, obviously 8, but letter B. So bromide, right? Okay, well, we have our benzene ring. It always takes so long to make benzene rings, like, you know, I'm never good at drawing. So let's just do that. And we're reacting it with with dibromo. Okay, so we can do this. And we also have hexene. Okay. Well, what do? Over here we have some hydrogens, and over here we also have some hydrogens. Our bromine can break that way, making this one partially positive and this one partially negative. And since he's positive, what happens? Well, since he's positive, this double bond can actually break off and attack him. Okay? It can attack him, and we can make this. Right? And then we still have a hydrogen, but this one is going to be a positive carbocation. Well, then that positive carbocation can be attacked by the bromine. Okay? And therefore, we would have something like this. Now notice what happened. I got rid of my double bond, and did I substitute my hydrogens? No. Did I add something with my hydrogens? Yeah, I did add something. I added a bromine. So notice that in the original compound, this carbon only had a hydrogen. But then in the new compound, this carbon has a hydrogen and a bromine. So this is referred to as an addition reaction. So we did an addition. Can my benzene do that? No, it can't, but my hexene can. So we can use this reaction to do what? We can distinguish between compounds. So we can say in the lab, okay, well, if this compound ends up being a dibromo, I know that it's not a benzene ring, because benzene rings only do substitutions, okay? So if it was possible and it's not, we would actually have something like this. We would actually have this compound. I'm not saying that it's possible, I'm just giving you an example. It would just be Br and then Br, right? So we substituted that. We got rid of the hydrogens and then somehow added a bromine. Is that possible? No, sadly it's not. So we could use B as a reagent, okay? So B would be the correct answer choice. So this would actually be a substitution. My hydrogens just became bromines, and that's not possible. So substitutions. Okay. Why would 1,3-cyclohexadiene undergo dehydrogenation readily? So why would it want to dehydrogenate? And what is 1,3-cyclohexadiene? Okay, well, first of all, it's a cyclic compound, so we can just do this. Wow, that's so perfect, my gosh. Really happy. So that's 1, 2, 3, and 4, so my fourth one's going to be there. Okay, so that's 1, 2, 3, and 4. And they're saying, why would it dehydrogenate? Well, that just means we're going to be adding another double bond on it. So over here we have two hydrogens, actually 4. And what if I did, I don't know, like H2SO4, right? What if I did that? If I did that, then one of my hydrogens can disappear, right? One of them can disappear and just make a double bond. And if I make a double bond via an E2 reaction, or E1, sorry, then what happens? It becomes aromatic. You see? It becomes aromatic. And aromatic just means that we have an increased stability. Also, we become conjugated. And also, we basically have our sp2 orbitals, right? We have our sp2 orbitals just communicating or connected. But basically, since we have conjugation and we just have an increased stability, okay? So I don't know what it means by it's easily reduced. They're saying like, oh, well, it has something to do with the hydrogens, right? But that wouldn't make any sense, right? Because reduction means that you have an increase of hydrogens. That doesn't make sense. We actually lost hydrogens. We were actually oxidized. So that's not true. That's false. Hydrogen is a small molecule. That's true, but it has nothing to do with it. Okay, 1,3-cyclohexadiene has no resonance energy. It does, kind of, right? We can actually do some resonance with just the original compound, so that does make sense. It would gain considerable stability by becoming benzene. Yes, notice that we can actually do a whole resonance, right? So if I wanted, I could do this, and that's the same compound. And since we can do a resonance, we could just do a circle in the middle, okay? That just shows resonance. So yes, D would be the correct answer choice. And E, it would not undergo dehydrogenation. That's false. I just did it for you. So this is false. It would do dehydrogenation. Okay. Number 10. Which of the following statements about whatever is not true? Okay. Well, first of all, how should I say? It's a really ugly compound. Okay, it's kind of like a boat. I don't know how to draw it out, but it's totally not stable. It actually has 8 pi bonds or pi electrons. And we know that 8 pi electrons means that it's not aromatic. It's actually anti-aromatic. How do I know that? Well, basically, it's conjugated. This compound is conjugated. And it has resonance, but because it has a weird number of electrons, 8 in this case, it would be anti-aromatic, okay? So, first of all, you have to be conjugated, and you have to have all your sp2 orbitals communicating. We're actually going to get into that later. But we have to have a good number of pi electrons. If we have 8, well, it's not good, and it would be anti-aromatic. So if it's anti-aromatic, we know that stability is going to go down. So stability go down, okay, it goes down. So it'd be E, because it's saying that, oh, well, this compound is super stable and it's as stable as benzene. That's not true. Benzene has 6 pi electrons, which is a good number, and that is aromatic. Okay, so that means that it's really stable, but this compound is anti-aromatic, which is not stable. Okay, so the answer choice would be E. Cyclopentadienyl is unusually acidic for a hydrocarbon. An explanation for this is the following statement. Okay, well, let's just do cyclopentadienyl, and actually I'm going to make some room. So let's draw out cyclopentadienyl. Here's my cyclo. And to make it conjugated, we can actually do this, right? So that's conjugated. It's not good because it's a 4 pi electrons. 4 pi electrons means it's, well, it wouldn't be aromatic to begin with, okay? We're not completely conjugated. It's weird. But over here, we have some hydrogens, right? Okay. Well, it's saying that we're really acidic, and acidic means that we're going to give up a hydrogen. So let's say sodium, right? And basically we're doing a very strong base, right? So we have sodium hydride or hydroxide. And if I give up my hydrogen, then what do we have? We have this. So here are my 2 electrons that left, and the hydrogen is now paired with the oxygen, making water, right? So there we have that. And we still have our double bond. But notice that this carbon gained electrons, and since we gained some electrons, we're going to be more negative. Okay, well, we're more negative now. So what happens? Well, what happens here, and we're going to get into kind of like the theory in molecular orbitals, is that we become aromatic. Well, what do you mean we become aromatic? We have 6 pi electrons now. Okay, we have 6 pi electrons. And 6 pi electrons means that it's pretty good. It's aromatic, but for it to be aromatic, we have to make sure that our p orbitals are communicating. And by that, I mean, let's do our balloons. And these are really cute balloons. I'm going to do a giraffe for you right here. And over here, let's do a polar bear. And over here, let's do Tata from a famous boy band, if you know that. And over here, let's do another balloon. Okay. So these are our pi orbitals. And notice that since we have a double bond, my pi orbital is going to be communicating. So let's fill it in right there. So he's communicating. And over here, since there's a pi bond, he's going to be communicating with this guy right here. So notice that they're both on the top. If the top balloon communicates with another top balloon, they're going to make a double bond. However, if the top balloon communicates with a bottom balloon, you don't have a double bond. You just have a normal single bond. Okay? We have a normal single bond. Okay? So this top balloon also communicates with this other top balloon. Right? And we have this right there. And notice that my electron can actually go here. Right? Okay. Well, Brian, I thought you said, you know, if you have a single bond, your top balloons are going to not communicate. Well, yeah, but what happens if I do this, right? What happens if I did this? Right? So I just basically moved my electrons, and it should still be the same, right? And it gets pretty messy, but you're going to have to take my word for it. So we could do this. And it's the same compound, okay? So don't worry about the balloons not communicating. As long as you have all your orbitals filled and they're shaded in correctly, we can label it as aromatic. So notice how all my balloons are communicating, right? We have a ring of green dots on the same side. They're all on the top. Okay, so that must mean that my sp2 is filled. So they're filled. Okay. Notice that we have conjugation. We have double bond, blank, double bond, blank. And technically the electrons could be a double bond. So you could say double bond right there. So bond, blank, blonde, blank, bond, blank. Okay, so we have conjugation. Okay, so that's checked. And then we have 6 pi electrons. So that must mean that we have a good amount of electrons. So Huckel, not Huckel. If you say Huckel, I'm going to cry. So Huckel's number is also satisfied. So that must mean, since we all have the 3 requirements filled, it means that we are aromatic. And that must mean that we have increased stability. Okay. So the reason why cyclopentadiene wants to give up this hydrogen is because it went from a non-aromatic, okay? It went from non-aromatic to aromatic. For it to be non-aromatic, you don't have conjugation, you don't have sp2, you don't have Huckel's number, you don't have one of these 3 requirements. For it to be anti-aromatic, You have the 2 requirements, but you fail at Huckel's number, okay? You have like 8 pi electrons. You have 12 pi electrons, right? That's not good. Yes, your sp2 orbitals are filled and they're communicating. Yes, you have conjugation, but your number is wrong, and therefore you would be anti-aromatic. To be non-aromatic, you don't have any of these, okay? Like, you don't have your sp2 filled, you don't have conjugation, and if you don't have any of those 2, then it doesn't matter about Huckel. Huckel doesn't matter, okay? To be aromatic, you have to have all these 3 requirements satisfied, okay? So the answer would be what? Let's see. An explanation for the following statement is what? The carbo... So they're removing... so 11, it would be C. So the removal of a proton from the cyclopentadiene would give you an aromatic anion. So aromatic anion means that this is an aromatic compound, it just has a negative symbol on it. So yes, it would be C. It would be C. Okay. Which compounds should occur with a decrease in pi electrons? And let's make some space. Okay, so we want a decrease, right? So since we want a decrease in pi electron energy, we want something that is aromatic. So decrease in energy means that we have aromatic. Okay. If we have an increase, so if we have increase, it would give us a well, not non, but it would be anti. It would be anti-aromatic. Okay, and if there's no change, then it's just non-aromatic. Okay, so that was pretty bad. So let's just write that. So non-aromatic. Okay, so we want a decrease, we want an aromatic compound. Over here, this is the most famous anti-aromatic that you'll ever see. Just have it memorized. It's cyclobutadiene. Okay, so right here, the reason why it's not aromatic is because if we do our pi orbitals, or our little orbital thingies, right? Let's do that. Yeah, they're all communicating. All of them. So let's do the top part. Right there. Right there. It's communicating. There we go. So yeah, all our sp2 orbitals are filled and they're on the same side. Then therefore we can have resonance, we have double bonds, etc. That's good. Okay. Is it conjugated? Well, cyclobutadiene is conjugated. We have a double bond, gap, double bond, gap, double bond. Okay. But what about the numbers? This is a 4 pi electrons. And the way I like to do it is that I don't like memorizing numbers. You have like, oh, 2 is this one, 4 is that one. I don't like that. I'm more of a math person, so we're going to do some calculus, okay? We're going to do some calculus 2. And the way I like to do it is we do 4n plus 2 is equal to pi electrons. Okay, so that's Huckel's rule. And if we do some calculus, we can do this. 4n plus 2 is equal to, okay, well, how many pi electrons do you have for cyclobutadiene? You have 4. Okay, so we have 4. So if I do 2 minus 2, we get 4n is equal to 2, right? If I solve for n, we have that n is equal to 1/2. Well, if n is a fraction, then I know that this is going to be anti-aromatic. So n is equal to fraction. I know that it's going to be anti. Now if n is equal to a whole number, then I know it's going to be what? Aromatic. Okay, well, that's basically the rule, okay? So over here, yeah, we have our things, right? Right here, our orbitals. And since we have a plus sign, what is that? A plus sign means that you just have, it's kind of weird, but just imagine your orbitals just being filled, okay? So over here we have this guy filled. He's filled. And for the plus sign, yeah, you can consider it as filled. Okay, so all our sp2 orbitals are filled. They're all communicating. That's good. But what number do we have? We have 4n plus 2 is equal to how many pi electrons do we have? 2. We just have 2. So now we have 4n is equal to 0. So if I subtract 2 on this side, I can subtract it from the other side. We have 0. So n is equal to 0 divided by 4, which is just 0. So yeah, n can be a whole number, and it can also be a 0, because 0, after all, is a whole number. It's technically a number, right? So this would be aromatic. So this is aromatic. And we do have conjugation. We have double bond, blank, technically a double bond, blank, okay? So the plus sign can act as a double bond. It's weird if you think about it. So that is aromatic, therefore it would have a decrease in energy and be more stable. It would be B, okay? So it would be B for that one. Over here, you're conjugated. You have 3 pi electrons. Well, 3 minus 2 is 1, and n is equal to 1/4, which is a fraction. That's bad. Over here, you have 4 pi electrons. So you have 4 minus 2 is 2, and now n is equal to 2/4, or rather 1/2, which is a fraction, okay? So 3 and 4 are wrong, okay? And yes, we'll be doing more Fuchel's rule later. I know this is kind of weird, but I want to do number 14 first before I explain number 13, because number 14 is going to do kind of like the groundwork and lay the foundation for understanding. So applying the polygon and circle method, also known as the Frost circle method, how many pi antibonding molecular orbitals are there? Well, we're going to have to assume, and this is why I don't really like the question, we're going to have to assume that we're working with benzene, okay? We're working with benzene. So here's my benzene. Right? And whenever you do this, basically you want to draw a circle on it. So I like calling it the Frost circle. So we have our cute little circle right there. Okay? And we're going to have to draw our pi orbitals on the bottom. So you can have something like this. And notice that I'm doing it on my points. So this point is going to have an orbital, okay? And this point is also going to have an orbital. Same thing for this guy. And same thing for that guy, okay? Whenever you're doing the Frost circle method, you always want your points pointing downwards, okay? And we're going to do that for number 13, and you'll see. So for conveniency, I'm going to draw my orbitals again over here. Okay? So that's a mood. So now we're going to have to fill in our orbitals. How many pi electrons do we have? Well, we have 3 double bonds, and each double bond is going to have 2 pi electrons, okay? So that's 2, 4, 6. That means we have 6 pi electrons, okay? So my arrows are going to be electrons. That is 1 electron. That is 1 electron. Together, they're going to make 2 pi electrons, okay? So here we go. The way I do it is this way. We do 1, 2, okay, 3, 4, 5, 6. You saw how I did that? I went from each orbital. So I put 1 electron, and then I went to the other orbital, and I put 1 electron. And then I went back to the first orbital, and I put my other electron, and so forth, right? Okay, so we used up all my electrons, and right here, this is going to be called the non-bonding. Non-bonding. You basically cut it in half, right? Going horizontally. Non-bonding. And this guy right here is going to be called the anti-bonding. So these 3 orbitals on the top are going to be called anti-bonding. Okay? So yeah, it would be D. 14 is D. This platform would be called the bonding platform. Right? And that's basically all you really have to know. So this is D. We have 3 antibonding platforms. Antibonding is also known as the LUMO, right? And these guys right here would be called the HOMO. Okay. So now back to number 13. Application of the polygon and circles technique shows that single electrons occupy each of the two non-bonding orbitals in the molecular orbital diagram of what? Well, that's a lot. It's kind of like word soup. I don't like that. Let's kind of dissect it. So first is asking us to do the circle method, okay? And it tells us that there's one electron in the top platforms, okay? So you remember the non-bonding platforms for the previous question? Well, there's only one electron in each platform, so it looks like this. Okay, but that must mean that this bottom platform is filled, okay? It looks like a face. But does that kind of make sense to you? I know that we have two non-bonding orbitals, so there's two of them right there. And they only have one electron each, so there are 4 pi electrons. So there are 4 pi electrons. That must mean we have 2 double bonds. Right? Okay. Well, benzene has 3 double bonds, so that doesn't make any sense, right? Okay. So, what can we do? What if I did this? Okay, well, you're saying that this is what? Cyclobutadiene. Well, does that make sense? So we have something like this. Okay, so that's 2 bonds, and there are 4 platforms. That's pretty good, actually. That's 4 platforms right there. But if I, again, this is why you want your vertices pointing downwards. If I do this, it would look like this, which is what we have, right? Hey, that looks pretty good, actually. Okay, well, why is C not right? Is cyclopropenyl cation? Well, cyclopropenyl cation looks like this. Okay, and if we did the orbitals, it will look like that. And you're saying, yeah, that looks good. Well, how many pi electrons do we have? 2. Okay, so 2, right? But then again, my positive carbocation means that we only have a hydrogen right here, right? So this carbon has a hydrogen, and that's it. So the electrons that it has is being used to make a carbon-carbon bond, this guy, another carbon-carbon bond, and a carbon-hydrogen bond. So we don't have any electrons to spare. Therefore, I only have 2 pi electrons. And there are no electrons in my orbitals, okay? So that wouldn't make any sense because I need to have my electrons like this, right? I don't have those. So cyclopropenyl cation would be wrong. What about a cyclopentadienyl anion? Well, cyclopentadienyl anion looks like this. And let's actually do it over here. Right, so 1, 2, 3, 4, 5, cyclopentadienyl anion. So yeah, it would look kind of weird, but let's just make sure that's right. Yeah, it's conjugated. Okay, so it will look like this. Right, so 1, 2, 3, 4, 5. We have 2, 4, 6 pi electrons. We have 6 pi electrons. Okay, so we have 1, 2, 3, 4, 5, and 6. Well, the issue here is that my non-bonding orbitals, the middle ones, well, they have 2 electrons, and I need them to only have 1 electron. That's the issue. That's not good. Okay, that's not good. So C and D would be wrong, and E, I don't really want to draw that because it's kind of like a weird. It's just weird to draw. I don't like it. So it's not C. It's not E either. So it would have to be A. Okay. So A would be the correct answer choice. Number 15. In which of the following compounds would the shortest carbon-carbon bond be found? Well, the shortest goes like this. Okay, well, I know that triple bonds are going to be super short. And next we have kind of like double bonds, which are medium. And then we have single bonds, which are long. Okay, so it's kind of like getting a stick, right? So if we get a branch from the tree, well, it's going to be a long branch, right? That's a single bond. But if I take that branch and I break it in half, well, the pieces are shorter and they're stronger, but they're medium length. Now, if I took one of those branches and I break that in half, I now have 3 pieces. Okay. Now, they're shorter, but they're going to be stronger to break if I try to break it all at once, right? So that's kind of like my logic. So if I have something that is a triple bond, I know that they're going to be short bonds. If I have something that is a single bond, I know that it's going to be a long bond. So let's see, I'm looking for the shortest one. Well, toluene, well, that has double bonds. That's okay. Ethylcyclopentene. Pentene means that it's a double bond. Okay, well, again, we have a diene, double bond, but now we have a hexyne. Hexyne is 3 of a kind. And 3 of a kind means that it's a triple bond. And I know that triple bonds are going to have what? The shortest bond length, but they're going to be the strongest. Okay, so hexyne is the shortest because it's a triple bond. So 3 bonds. And I know that it's super short, so it'd have to be D. Okay. 16. Which of the following statements regarding the Cyclopentadienyl Anion is right? Okay, well, the Cyclopentadienyl Anion. Let's draw this. Okay, so there we go. We have, how many pi electrons do we have? We have 4. We have 4 pi electrons. Okay, we have 4 pi electrons. If you want to get your practice in, we could do this. Okay, so therefore it has 2 non-bonding pi orbitals, which have 1 electron each. It has 1 bonding pi orbital with 2 electrons, and then it has 2 anti-bonding orbitals. Okay, right. So what is this? Well, is it conjugated? Yeah, it's conjugated. Okay. Let's see. So it is conjugated, but is it aromatic? Well, no. So we have conjugation. All our sp2 orbitals are filled. But does it follow Huckel's rule? No, it doesn't, because we have 4n plus 2 is equal to 4 minus 2 minus 2. We do 4n is equal to 2, therefore n is equal to 1/2. Well, that's a fraction, and I know that since it's a fraction, it's not going to be aromatic. Okay, well, A is saying that it is aromatic. Well, that's not right. That's false. B says that it's not aromatic. Well, it's conjugated. It has, some pi electrons or whatever, but it's not going to be the same number. It's not a good number. 4 is not a good number, okay? Since 4 is not a good number and it gives us a fraction, it's not going to be aromatic. In fact, it's going to be antiaromatic. So we have conjugation. If you were to do your balloon animals, you would have your sp orbitals all filled, which is good, but we don't have 6 pi. We don't have 2 pi. We don't have 10 pi either. We have 4 pi. That gives us antiaromatic. So it is B. Okay? It obeys Huckel's rule? No, it doesn't obey Huckel's rule. Huckel's rule tells you that if n is a whole number, it's going to be aromatic. Okay? But n is a fraction, and that's not good. So C is wrong. It undergoes reactions characteristic of benzene. So it's saying that this behaves like benzene. No, it doesn't. Benzene has 6 pi electrons. This has 4. That's bad. It has a closed shell of 6 pi electrons. Again, this is 4 pi. So that's bad too. So the answer choice is B. Which of the following would you expect to be aromatic? Okay, well, instead of doing the balloons, because that would take about 16 hours, I'm just going to draw some dots, okay? And these dots show that they're going to be communicating, okay? So you can assume that these dots are going to be communicating on the same side. Well, let's draw our balloon animals. We have a dot right here, a dot here, a dot here, and here, and you can consider a dot over here too, okay? So our sp2 orbitals are filled. We have conjugation. We have double bond, blank, technically a double bond, and then a blank. Okay. And now we just have to go through Huckel's rule. Right here we have 4 pi electrons. Notice that my carbocation doesn't contribute to the electrons, okay? It's like a blank. So we have 4 pi electrons. And we know that 4 pi is bad, right? That's going to give us a fraction. So I know that 1 is not right. Right here we have a dot, and a dot, and a dot there, so they're communicating. How many electrons do we have? 4. So we have 2 electrons from the double bond, and then we have 2 electrons from the anion, so that's going to be 4 pi as well, right? So that's 4 pi. That's bad. Over here, this is a famous, super famous antiaromatic compound, and the reason why is because we have our sp orbitals checked out. We're conjugated, but we have 4 pi electrons, so that's bad. Number 4, we're communicating over here and there too. But now this carbon doesn't have any electrons to give up. All its available electrons are making bonds. So they're making carbon-carbon bonds, carbon-hydrogen bonds, etc. So there are no lone electrons to make double bonds, right? So first of all, this is non-aromatic. It's non-aromatic because we don't have our sp2 orbitals filled, okay? Right? So if you don't have your sp2 orbitals filled, that's it. You don't even have a chance to be conjugated. That's it. That's done. So that's non-aromatic, actually. So we're going to call that non-aro. Okay? So that's not right. What about 5? Well, over here, we have some communication, and we have communication on the carbocation. Now we have 2, 4, 6. We have 6 pi electrons, right? We have 6 pi electrons. I don't know why there's a dot right there, but it's kind of... Actually, yeah, that would make sense. So we have 6 pi electrons, 6 pi. So if we do 4n plus 2 is equal to 6, so we subtract 2 right there. We have that 4n is equal to 4. If I divide this by 4, divide that by 4, we have that n is equal to 1. And 1 is a whole number last time I checked, right? So since 1 is a whole number, this is going to be aromatic. We have our sp2 orbitals filled, we have conjugation, and then we have a whole number. So that must mean that this is aromatic. So number 5, or E, would make sense. Yeah, so it would be answer choice E. And that's a very bad E. Super ugly. E, or 5. Which of the following would you expect to show aromatic character? Well, first of all, number 1 would be wrong. It's not conjugated. Okay, so you could just look at it and see that it's not conjugated. We have double bond, blank, double bond, blank, double bond, blank, blank. That's not good. Okay, so 1 is wrong. It's not even a chance. What about 2? Well, you're probably saying, Brian, this isn't conjugated because, well, look at it. It hits double bond, blank, double bond, blank, double bond, blank, blank. I get it. I understand. But what happens if we move this bond to the oxygen, making this one negative and this guy positive? So what happens if we do that? You're probably like screaming or something. That'd be cool. See, this is why I don't like drawing this. Let's do this. Right? And I guess kind of like an oxygen here. 1, 2, 3, 4, 5, 6, 7. Yeah, it works, I guess. So this one's negative, and this one's positive. Okay, well, now this actually is conjugated. Notice that we have double bond, blank, double bond, blank, double bond, blank, and then we have a carbocation, and then blank. So that does allow us to do conjugation, right? So Now we have our dots right here. That just shows communication. Right? And that's pretty good. So now we can actually do our Huckel's rule because we have our sp2, we have conjugation, now we have to do Huckel. We have 6 pi, and you already know the answer. This is very common. 6 pi electrons, you know that it's going to be conjugated, or I'm sorry, you know it's going to be aromatic. So this is aromatic. Okay, so just know that whenever you have a carbonyl or an oxygen, like over here, you can actually move the electrons towards the oxygen to make a carbocation, and that carbocation can do resonance, okay? And it can basically do conjugation. So 2 is right. This is right. This is good right there. Over here, we do have conjugation. Our sp2 orbitals are filled. That's good. But what about it? We have 2, 4, 6, 8. We have 8 pi electrons, and that's not good. So 4 pi, or 4n plus 2 is equal to 8. Therefore, 4n is equal to 6, and n would be equal to 6/4, okay? Which I believe would be like 3/2 if you divide it by 50, I guess. I don't know. So 3/2. I meant divided by 2, obviously. But that's a fraction, and that's not good. Okay, so 3 is wrong. Over here, you have 2, 4, 6, 7. 7's really awkward. It's just really awkward. So again, 4n plus 2 is equal to 7. Therefore, 4n is equal to what? 5? And would equal to 5/4. Again, a fraction. It's ugly, ill. Don't mess with it. So the answer choice would be B. On the basis of molecular orbital theory and Huckel's rule, which molecules and or ions should be anti-aromatic? So we're looking for something that is anti-aromatic. Again, number 1 is going to be super famous, so that is anti-aromatic. I know that 1 has to be the answer choice. So C, D, and E are wrong because they don't have number 1. That's anti. So now it's either A or B, okay? And I know that 5, because they're common in both A and B, has to be anti-aromatic, right? Okay, so now I just have to make sure that 2 is anti-aromatic. So first of all, we do have some conjugation, or I guess my orbitals are filled right here. So let's do right here. Okay, so they're filled, but then we have 4 pi electrons, right? So we have 4 pi, and we know that 4 pi is going to give us a fraction, which is anti-aromatic. So that is anti. Okay, that's anti-aromatic. So again, our sp2 orbitals are filled. We have conjugation, so it's double bond, blink, double bond. Technically, the lone pair could be a double bond. It can act like it. But then our Huckel rule, or Huckel's number, is a fraction. Okay, so that's not good. It's not good. So this is good. That's good. And just kind of like for conveniency, we're going to do number 5 as well. Over here, we have communication. So my orbitals are communicating to make double bonds, etc. That's good. And we have conjugation as well. But we have to check the number. So we go 2, 4, 6, 8. Again, that's 8 pi electrons, and that's not good, right? So that's going to give you like some weird fraction. And therefore, it is anti-aromatic. Okay, so that is good. 1, 2, and 5 would be the correct answer choice, aka B. But now let's do the rest, because I'm a completionist and I want you to distinguish between non-aromatic, anti-aromatic, and just aromatic. Okay, I feel like that would help you out, hopefully. So right here we have some communication right there, but then my third carbon is not going to be communicating, right? He's not communicating, so there's no conjugation. If there's no conjugation, then there's no Huckel's rule. There's no anti-aromatic. There's no aromatic. Therefore, this would be non-aromatic. Okay, so that's non-aromatic. It fails the checklist. Okay, so anti-aromatic passes the checklist, but it fails at Huckel. Okay, so we go 2, 4, 6. So that's 6 pi electrons already. So that's 6 pi. We are conjugated. We also have our sp2 orbitals filled, and it's 6 pi, so you know it's going to be aro. That's aromatic. Over here we have 2, 4. Now you're probably wondering about the nitrogen. Don't worry about the nitrogen. Just treat it like some electrons, okay? Just treat it like 2 electrons. So that's going to help us out. Okay, so this technically is communicating. So 2, 4, 6. We know that 6 pi is also aromatic. So that's aromatic. And I believe that is called pyridine. This is pretty cute, I guess. How weird am I thinking that compounds are cute? It's pretty sad. Now we have 2, 4, 6, 6, and then 8, 10. So we have 10 pi electrons. 10 pi electrons. Our orbitals are communicating. We have conjugation, but we have 10 pi electrons, so that's kind of weird. Let's make sure that it's right. So we have 4n plus 2 is equal to 10. Okay, so 4n is equal to 8, and therefore n would have to be equal to 8 divided by 4, which is what? 2. Okay, so 2 is a whole number, and therefore it would be aromatic. All right, what about this one? 2, 4, 6. Well, we have 6 pi electrons, but that doesn't matter because we're not conjugated. We don't have complete communication. Okay, so if it's not conjugated, we know that it's already non-aromatic. What about this one? This one does communicate, and it has 6 pi electrons, and you know that 6 pi electrons is going to be aromatic. So that's how you distinguish between aromatics, non-aromatics, and antiaromatics. Hopefully that helps you on your exam. So which of these is not an aromatic compound? Again, you're dealing with heterocyclic compounds, basically compounds that don't just have carbons, they have oxygen, nitrogen, etc. You treat them like basically electrons, okay? So that's 2, 4, 6. So I just said the double bond is 2, the nitrogen is 2, and the oxygen is 2. So we have 6 electrons, and they communicate normally. Okay, so 2, 4, 6. You already know that this is aro. Again, 2, 4, 6. That's aromatic as well. That's going to be aro. Over here, this is kind of famous because I just did it. You can pull this guy over here to make him negative, and this one's going to be a positive carbocation. So that means that he communicates. Let's do that in a different color. That he's doing some communication. Okay, so that is 2, 4, 6. That's 6 pi, and you know that this is aro. So it cannot be that. Okay. And now look at number 4. Well, number 4 is not even conjugated to begin with. We have 2 gaps. We have double bond, gap, gap, double bond. That's bad. This is not aromatic. It doesn't have communication. Okay, so look at it. We don't have a communication. Okay, so number 4 is bad. This is non-aromatic, which is the correct answer choice. And number 5 is just aromatic. 2, 4, 6. 6 pi. We know that this is aro. Which of the following compounds would you expect to be anti-aromatic? So not too bad. 2, 4, 6. We know that this is aromatic as well. Yeah, it gets pretty simplistic once you get used to it. So we are communicating. We're conjugated. We have 6 pi. We know that this is aromatic, so that's bad. You already know it's 3. Like, that is like the super famous anti-aromatic compound. Over here, right there, conjugated, communicating, we have 2 pi, right? So 2 pi is good because you're going to have n of 0, which is a whole number. So we have 2 pi, and that's aromatic. This one is communicating as well. There's conjugation, but we have 4 pi, and 4 pi is anti-aromatic. So this is the correct answer choice right there. Benzene, you know it's aromatic because there's communication, there's 6 pi, there's conjugation, it's good. So that's bad. We are communicating, we are conjugated, and there's 6 pi. Okay, so we know that this is aromatic as well. Okay, so the answer choice would be C, or 3. Okay. Now, which of these would you expect to have a significant resonance stabilization energy? So basically, ignore this. Which one is, oh, how can you say aromatic? Right? It's ridiculous. Just cross it out and just say aromatic, because aromatic compounds are going to have resonance stabilization, okay? And we know that this has to be aromatic. Okay, 2, 4, 6, 6 pi. We know that it's aromatic, so that's good. Same thing here. 2, 4, 6, 6 pi. That's good. And then 2, 4, and 6 right there. So that's 6 pi. That's good too. So all of them are aromatic. They're going to have stabilized energies. And they're all perfect. So D would be the correct answer choice. D, right there. Which of these species is aromatic? Okay, well, this is not conjugated. Okay, so that cannot be the correct answer choice. That is non-aromatic, non-aro. Okay. This is not conjugated, so that's non-aro. Right here. Let's see. We have conjugation and communication. But what about our Huckel's number? 2, 4, 6, 8. This is 8 pi. Well, since it's 8 pi, I know that it's going to be a fraction, and that's not good. You want a whole number, so that is antiaromatic. Anti. And what about this one? This is not conjugated. Well, actually, bond blank. Well, yeah, it would be not conjugated as well. So we have communication there, but not really here. So that's not good either. Right? So it's not conjugated to begin with. Anyways, who cares? Over here, we can break this bond to go towards the oxygen, right? Making this a negative compound. And we can make a positive carbocation right there. So we have communication. So now we have 2, 4, 6. We have 6 pi. And we know that 6 pi is aromatic. So the answer choice would be B or number 2. Which aniline would you expect to not be aromatic? So in this case, we basically want something that is anti-aromatic. So we have 6, right? So for letter A, we have 4n plus 2 is equal to 6. So 4n is equal to 4. Then 4n is equal to 1. So that is aromatic. So that's wrong. That's aro. 14. 4n plus 2 is equal to 14. 4n is equal to 12. Therefore, n would have to be equal to 3. So that is a whole number, so that's wrong. What about 16? Well, 4n plus 2 is equal to 16. So it's 16. 4n is therefore equal to 14. N is equal to 14 over 4. That's a fraction. And since it's a fraction, we know that it's anti-aromatic, so it has to be C. C would have to be the correct answer choice. What about D? Well, we have 4n plus 2 is equal to 18. 4n is equal to 16. And n is equal to 4. That's a whole number, so we know that this is aro as well. Okay. And then finally 22. We have 4n plus 2 is equal to 22. 4n is equal to 20. 4 is equal to, n is therefore equal to 5. That's a whole number, therefore it is aromatic. And so if your professor gives you an aniline of like 2000 whatever, well, you already know that you could just do Huckel's formula and figure out the correct answer choice. If your n is a whole number, it is aromatic. If it is a fraction, like 4/5, then it's anti-aromatic. So 16 in this case would be a fraction once you do the formula. So the answer choice would be C. Hopefully this video helps you. I hope you do well on your exam. I hope you continue to study and that you have a great day. And that someday you'll be happy or something. Thanks for watching, and I hope you have an amazing day. Thank you.